Okay, well, I believe this is live now. Hello and welcome to Transform 2020. This is a huge moment for all of us at Software Underground, and I'm really delighted to welcome you to this Getting Started with Python tutorial/demo. So first of all, the audience is really aimed at beginners, and I'll talk about that in a second. My name is Rob Leckenby. I'm a digital geoscientist. I work for Agile Scientific. So I really want to scroll up here and make sure that everyone knows they're welcome. And in the strange times we're living right now, you are welcome, whoever you are, wherever you are. And I want you to feel that you can say anything and ask anything. We'll talk about the chat and where you can communicate with us in a second. So as I say, this session is open to everyone, but it's really aimed at people who've either never coded at all, or who perhaps are coders but don't know Python. And so there are some videos that we set up for Windows and Linux. I'm sorry I didn't make one for Mac. And there's also links in there for an installation guide for the tutorials. So if you're watching this in the future, you'll have access to the repo, so the data that I'm going to show you and the notebook I'm going to show you. And you'll also have access to how to run it on your machine. Now, first of all, I want to thank everyone that's watching this. I have no idea how many people are watching right now or how many people will watch in the future. And I'm 20 seconds in your past as I'm talking because of the YouTube delay. So, so here we go. The agenda for today, we're starting now. Because it's a 3-hour session, I will have to take at least one break, maybe two, otherwise my voice will give out. The break times are going to be fluid because it'll depend how far I've got down into this demo. And when there's a break, there'll be a placeholder that comes up on screen telling you there's a break, and then another one hopefully telling you when we're about to start again. So you'll be able to stretch your legs as well. Okay, so first content, and then I'll talk about setup and a bit of the organization that's going on behind the scenes and how you can interact with us. So as I say, this is a demo, and we're going to start off with simple math, logic, and flow control in Python. I'm not aiming to teach you Python here. We actually do that and elsewhere, and you can find many, many resources online. What I'd like complete beginners to take away from this is not so much the syntax that we'll show you, but rather see 4 or 5 cool things that you can do in the geosciences with relatively little code. So please don't focus on every comma or equal symbol, but rather focus on the output and the fact that you can reach that output with relatively little code. So for that, we'll start, as I said, with simple math, logic, and flow control, but then we'll look at examples of equations that I've used quite a lot in my professional career as a geologist. But just as an example of how you can take science and turn it into Python. Then we'll kind of take a tour through the geosciences, going through geophysics, mapping digital elevation models, looking at well data, so well log data, and we'll end up hopefully scanning through a seismic cube using Equinor's segyio library together with matplotlib. So that's the journey that I propose that you take with me. And now, how do we get started? Well, hopefully, if you're watching this in the future, you'll have plenty of time to pause the video and see how to get started. So hopefully at the bottom of the screen now, you should see some short links. First of all, to the repo, so where I've got this these data saved on GitHub. And secondly, to the channel on Slack, where you can join the conversation. And so that conversation will be, how can I say, not even curated. Martin will be there to welcome you, is what I'm trying to say. So Martin, so he's MTB-ZA on Swan. And if you have questions about what I'm doing, he'll be able to answer you, and he'll be watching the live stream with you. Okay, so in this demo, I'm using Anaconda. And so the first thing I've done is I've created an Anaconda environment. And as we say here, An environment is really nothing fancy. It just contains a collection of Conda packages that you've installed. And so we can use these environments to isolate different projects. So throughout the tutorials in Transform 2020, most of the presenters will be using Conda, perhaps not all. And so if you start with the environment we're making now, you should probably be able to add to it for those tutorials or simply recreate new ones. So the first thing I did was I created an environment, that I called Transform 2020. I chose a version of Python. I'm using 3.7, so of course 3.8 is out now. And if you are using 3.8, I believe all of this should still work. And in this tutorial, I've installed the whole Anaconda package list inside this environment. So it is rather large, and for sure I am installing things I will not be using in this tutorial. Now, as well as this, I wanted to introduce you to 3 libraries that I think are very useful in the subsurface world. One of them is Welly. So Welly deals with LAS files, so log data LAS files. Of course, there are also different kinds of LAS files, but this is for log data. segyio I've mentioned briefly before. So this is published by Equinor. And this really allows you to do the input-output of segyio files and converts them into NumPy arrays, which we'll meet a little later. So for now, I appreciate that's just jargon, but bear with me and you'll see what this is. And finally, Bruges. Bruges is really a collection of geophysical equations, but actually at the moment in Transform 2020, people are adding more functionality to Bruges. So it could become a hub of basically subsurface functions that you might want to use in Python. So that's the objective. And now we've created that Conda environment, we need to activate it. So these are all commands you need to run in a terminal or an Anaconda prompt. And there are demos of how to do that on the Swan channel on YouTube. So we activate the environment, and then we have to install those libraries into that environment. And you can do that in different ways. In this case, I'm using pip, which is part of the Python standard distribution. And so with pip, I'm installing Welly, segyio, and Bruges. You'll have to tick yes, you'll have to agree to install all of these, of course. Now, as you see, I'm in a web browser right now. I'm using what's called a Jupyter Notebook. And so for those of you who are not familiar with it, a Jupyter Notebook allows you to run different programs, Python being one of them, and essentially mix code, output, and formatted text. So I won't go into the details of Jupyter Notebooks. Suffice to say that once I've created this environment, I need to make it available to my Jupyter Notebook. And there are 2 ways that I've listed down here for you to do that. One of them is another pip install, where we're installing NB-Conda kernels. And then once we run Jupyter Notebook to start the Jupyter Notebook instance that we're looking at here on screen, you'll then have access to the new environment you've created, and I'll show you how in a second. And the second option, which is the one I'm using here, is we're using Python. We're then using the IPY kernel module that was installed when we created the environment with Anaconda. And in that module, we're using the install function. And for the current user, so --user, we're installing the current name, or the name of the, sorry, not the current name, the name of the environment we want to use. So in this case, Transform 2020. Okay, so once we've done that, we can now activate those environments or choose them in our Jupyter Notebook. And to do that, you'll have to go to kernel, change kernel, and then select the kernel that you want to use. So Transform 2020 in this case. And then you'll see top right of your browser, there'll be the name of your environment. So if you've called it something else, you'll have the name that you picked there. So hopefully everyone's with me. And of course, if you're watching this live, you might not be able to follow all the live coding I'm doing. But if you are watching this in future, by all means, pause the video and make sure you've got your installation set up before you continue. So you'll notice that I'll take quite a few drinking breaks just to soothe my voice as I go. Okay, so the first thing we're going to do is look at a bit of basic Python. And as I say, I'm not going to teach you Python, but I just want to illustrate some of the things we can do with it. So let's start by doing some simple mathematics, right? So we can do division, multiplication, addition, all the kinds of things you would expect. But here you see that we're simply multiplying two integers. Now, likewise, we could multiply integers and what are called floats. So this is a float. It has a decimal point. But you might not always want to have or to type in the actual number. So very often we'll have what you might refer to as variables in mathematics, and in Python, those are called names. And so to define a Python name, if you will, we'll choose a name. So let's say A, and we can then assign it to or assign a value to that name. So I can say A equals 3, for example, B equals 4.12, as we had just a second ago. And then I can do A times B, no surprises, hopefully, and I get the same result as if I was just passing the numbers in directly. Now you can also mix these together, so I can do A times B plus 4. That's not a problem. I can mix all of this kind of things around. So all the operators that you might expect are in Python. There are several that you might not expect, but we'll mention them if we come across them. So you'll see in this demo, there are a few exercises dotted throughout the notebook. By all means, have a go at them yourselves. If you're watching this in the future, pause the video and try to do it yourself. But of course, I'll carry on and just show you how we can do this. So the first thing we're going to do is we'll take a simple equation, t equals xy plus z, and we'll write that equation as a line of Python code, and then see how we can define it and use it. So down here, the first thing I'll do is I'll say, okay, x equals 3 as we had before, y equals say 10, and z equals 1. And so now what I can do is I can say exactly like we have above the exercise, I can actually write that out. So I can say t equals x times y plus z. And finally, if I look at t, so if I ask Python to show me the current value of t, I get the value that I expect. Now, I'm sure you'll agree that this is all well and good, but it's not very practical if I want to reuse that. So say I wanted to calculate this again, but with different numbers, I'd have to rewrite those 5 lines of code again. And sure, this works, but again, it's not what you want to achieve. So there is a concept in coding called dry. Don't repeat yourself. And clearly that's what I've done here. So all programming languages, or most programming languages, give us a way to define functions or subroutines, if you will. And so that's what we're going to do. So what we want is to have a function that we'll call compute t. And we want to be able to pass any combination of 3 values to it and get t back with using this equation here. So how do we do that? Well, we need a keyword, def, that will define a function in our current Python interpreter. Then the name of the function, and here we've already chosen compute t. Now, I should say the name of a function should start with a lowercase letter, no numbers and no uppercase letters. And there should be no space in the function name. So you notice here the use of the underscore. Then after that, I will call the function or put parentheses after the function and have my placeholder values inside of here that will then be passed to the function. So let's say x, y, and z, for example. And then all functions should have some documentation. So we'll say, for example, that we're combining the inputs as a times b, as a times b plus c. Okay. So x, y, z, a, b, c, those are all internal to the function. What they might be called outside of the function is not related to what they are called in here. So I can now calculate the result. Actually, to be consistent, let me call it t. And so I can say t is equal to x times y plus z. And in a function, you will generally return something. And so here I will return t. So I'll now run that cell. And as you see, I get no output. So in a Jupyter notebook, every time you run a cell and it's been executed, you have an in with an integer value. And if that cell returns something as an output, you will have the out with the corresponding out integer value. When I define a function, I don't get this out. However, there is an effect. So if I now come to my compute t function, and in a Jupyter notebook, hit Shift Tab, you see that I have access to the docstring. So this docstring, of course, is very short, but you'll find in libraries such as Pandas or NumPy, you have excellent docstring, excellent documentation that will show you not only how to use the function, but how it's been built, often some examples, some references for scientific equations and so on. So this function is now available to me, and I can run this cell with Shift Enter, and that works. I can run this next cell again, Shift Enter, different value, and as you see, I've not had to retype all this X, Y, Z, T, etc. Now here I'm passing, of course, numeric values, but there's nothing to stop me from passing variables that I've predefined. So A, B, and 5, no problem at all. Okay, so I'm just passing single values to this function, and I'm sure you'll appreciate in geoscience we often want to pass lists or longer vectors of data. So there are various ways we can do this. The first one I'll show you is part of the Python standard library. So what I'm going to do is I'm going to define some values in a list. And so a list is part of the Python standard distribution types. It's one of the primitive types in Python. So I'll make a list here. And then once I have that list, I can actually loop over it. And I'm going to show you this in contrast to using NumPy in a second to show you how we can pass not a single value to one of these functions, but multiple values. So here, for example, I could say for each value in my values list, I would like Python to print out that function that I've defined, so compute t, but passing into it, let's say, the value, so 0, 1, 2, 3, 4, and then 10 and 1, for example. And you see here that I'm now no longer passing a single value in my function, but I'm passing one after the other, a single value, iterating over this container, this list. Now, this is great, of course, but there's a library that you will always see in scientific Python called NumPy. So NumPy is numeric Python, or stands for numeric Python. And NumPy is part of the environment that I created, but I have not imported it yet. So I don't yet have access to NumPy. I need to import that in my notebook. So for that, the canonical way of importing NumPy is to import it as NP. And you see when I import again, I get an in with an integer number. And I can now make an equivalent structure to the one I had here with NumPy. And you'll find that I don't need to use this loop in order to use it. So I will make X, and I will say that, X is a NumPy array with the same values I had before. So 1, 2, 3, and 4. I'm sorry. And if I look at X now, you'll see that to all intents and purposes, they are the same data than in values, but they now sit in this new object called an array. So we can do this actually in other ways too, rather than passing in the values arbitrarily like this. NumPy allows us to build these kinds of structures on the fly, as it were. So I can say, give me an array range up to 5. And then if I look at X, once again, I get 0, 1, 2, 3, 4. So you'll notice that in NumPy very often, in a lot of Python, intervals are half open. And so I'm going from 0 up to 5, but excluding 5. So, okay, that's all well and good, but what can I do with X? Well, remember before when I was calling compute T, I was passing single values, 2, 3, 4, A, B, C. Now I'm passing these five values as X. And you see that I automatically get this broadcasting of the calculation across each element of my array. So you're going to see NumPy quite a lot in this notebook. And as I say, I'm not trying to teach this to you, but simply to show you that with relatively few lines of code, we can achieve quite a lot. So, okay, so that's pretty nice. What if we wanted to check for conditions? So there's another statement I want to show you before we actually go into transforming some scientific equations into Python. And that's the if statement. So as before, I can iterate over X, for example. And if I print X, I will get each one of those. Let me say values. Oh, I changed values, didn't I? Yes, for value in values, and I should print value. So 0, 1, 2, 3, 4. Now what I can do is actually do a check on this value and say, in a certain condition, do this, in another condition, do that. So we do that with an if-else statement. So for example, I can say if value is, I don't know, greater than 2, then we will print out, as we did before, the compute T of our value and 10 and 1. And so I can comment this line out by putting a hashtag in front of it, and then it's just not run. Excuse me. So if I run this code, you see that I only got a printout for those values above 2, but I got nothing for the values below 2. So what you can do is pass an else statement where I might say print, and here I could say, let's say a message that says small number, no value computed, for example. Okay, so of course I'm not showing you everything that's going on in Python or that you can do in Python clearly, but I just wanted to illustrate a few simple structures that we find. So the fact that we can do simple mathematical operations, the fact that we can iterate, loop over data, and that we can put conditional statements in our code. And likewise, the fact that NumPy, which is ubiquitous in Python, NumPy allows us to sidestep some of those loops by broadcasting operations element-wise across the array. So let's see how that actually works in practice now. So what we're going to do, excuse me, is take Darcy's law and turn it into a Python equation or Python function. So I'm referring to Darcy's law as it's listed on Wikipedia. There's a link in my notebook here if you wish to refresh your memory. What we're calculating is flow rate, and that depends on the permeability of the sample, its cross-sectional area, the viscosity of the fluid that we're considering, the length of the sample, and the pressure difference across the sample. In this exercise, all units that I'll show will be SI units. And so the exercise now is to turn this into a Python expression, either as we were doing before with the t equals x times y plus z, or as a function like we've just seen the compute t example. So I'm going to do both just to illustrate how we can go from a simple set of Python code and turn that into a function. So the first thing we'll do is we'll define all of our parameters or arguments, give them values, then run the calculation and look at the output. So for now, I'll keep basically a 0 flow with unit properties across my sample. So I'll say K for permeability equals 1, uppercase A for area equals 1, mu for dynamic viscosity equals 1, the length of the sample will be a unit length, and dP will be 0. So I've got no pressure difference across my sample. So what I expect is the flow rate to be 0. So let's calculate the flow rate using Darcy. So it's going to be K times A times dP divided by, and then we can use parentheses to group things, by mu times L. So K times A times dP divided by mu times L. And if I now look at Q, I expect 0, and indeed I get 0 back. Now you may notice I'm getting 0.0, that's simply because I'm dividing, and when I divide with float division, with the standard division in Python, I always get a float back. Now, of course, here we're hitting the same issue we had before, so let's put this into a function. So as before, we define a function, and let's not call it Darcy, let's call it what its output is going to be. So let's say the flow rate, that's what we want to get back from this equation. And now we need to give to that equation all the inputs that it needs. So we'll use the same nomenclature, K, A, mu, capital L, and dP. And again, I'm going to put a doc string in here, but just so that I'm not typing all this out, and you'll see me do this a couple of times. I'm going to copy something from my other monitor here, paste it in here, just to illustrate that we actually do want a doc string and show you a little more than we had a second ago. So the first thing we have in a doc string is what this function actually does. You might then have references. So here, for example, a link to the Wikipedia page for Darcy's law. We might state the kind of arguments we have in there, so permeability, the units, and what we return. Now, furthermore, and I've not done that here, you might actually put in what kind of Python types you're using or you're accepting in your function. I'll leave that for now, but that's something that becomes important as we move forward. So now what do? Well, I actually take the exact same function I wrote before and simply drop that into my function definition. And then I need to remember to return Q. So as before, if I run this code, nothing immediately happens. I don't see anything. But now I can, first of all, auto-complete that function. And if I run Shift Tab on there 4 times, I get a little box down at the bottom that actually shows me my doc string with all the references and all the information I put in there. I cannot stress enough how important doc strings are, whether you're new to Python or not. Writing code is, once you get used to it, can be rather quick if you're trying to solve a simple problem like this. But then remembering what you're doing 6 months down the line can be more challenging. So now we've got this function, let's use it. And so I'm going to put in the values that I had before, the exact same values. So, and actually I'm going to just put 1, 1, 1, 1, and 0. And so these are what are called positional arguments. And so Python is reading this and it's assigning in turn each value to the corresponding positional argument in the function definition. So if I run this, I expect 0 out as before, and indeed that's what I get. Now, we're not writing tests at this point, and that would obviously be a large part of writing more professional code. But as an illustration, hopefully this is useful. So now let's put in some more realistic values into our function and see what comes out, see if the values that come out make sense to us and how we can expand this and maybe plot it. So first of all, I'm going to consider sidewall core. I don't know if everyone's familiar with this kind of these kinds of samples. Now the sidewall core I'm showing you this is not the one from which I've taken these values. And these values are simply chosen arbitrarily. This is simply to show you what I'm talking about. So it's a plug of rock that's generally been cut into a full-size core. And we're going to run some experiments on that plug of rock. In this case, as no doubt you can tell, this went under some triaxial testing for geomechanics. So not for fluid flow. So what we're doing here is we're saying that we've got a 500 millidarcy permeability, a 1-inch diameter plug, so that would be the diameter across this section, a dynamic viscosity of water at room temperatures, a 2-inch length long plug, and we'll put a DP, so a pressure differential across the sample of 100 psi. So if I now calculate Q using my flow rate function with these values and print out the result, I get that the flow rate Q is going to be approximately 0.05 cubic meters per hour. And so that hopefully should sound about right. Now, again, here I'm using single values. And while I don't want to delve into the details of how I'm going to do the next thing, I just want to illustrate that with a single line of NumPy, we can turn this single value of L, for example, into a whole range of L values. So remember, we have NumPy, so I can do NumPy A range. And let's say I want to go from 0.05 to 1 in steps of 0.05. Now, if I run this, I get back this array, all these values of length. So let's save that into a name. Remember, a name is like a variable in Python. And so now if I look at that, L is this array. And so I can rerun my code, flow rate of permeability, area, viscosity, length, and pressure differential. But this time I'm running it on this whole array. And I'm multiplying it by 3,600 simply to get the flow per hour. So I've calculated that. I now have Q. And it's now time to introduce to you the, let's say, the mother of all plots in Python. I guess most of them start with matplotlib, and people go much, much further than this. But matplotlib allows you to plot data extremely quickly, extremely easily, to look at the data that you've gathered or that you're trying to analyze. So the import statement should look similar to what we had before when we were importing NumPy. So I'm importing the pyplot module of matplotlib as PLT, and this is the standard way of importing that. But on line 1, you see this % symbol followed by matplotlib inline. So that is what's called a magic command inside of Jupyter Notebooks. And what this will do is it will allow us to visualize plots directly in the notebook rather than in a second window. The next thing I'm doing is I'm running plt.plot, to which I'm passing x, y values. The x will be the length of the plug that I'm looking at, and the y will be the flow rate. And if I do this, I see the drop-off that I expect as a function of the length of the plug. So the longer the plug for a given pressure differential, the lower the flow rate through it. So that's fine, and hopefully you agree that a single line can already show us quite a story. However, we want to dress this plot up somewhat. So we want to make it a bit larger, make it more legible, add some labels to it, and so on. And so again, matplotlib allows us to do this relatively simply. So what I'm going to do, is here I will add a few lines. I'm only doing this so that I'm typing in the middle of the screen and you don't get distracted by what I've got down below, and then I'll delete the superfluous lines afterwards. So what we want to do is take this plot and make it bigger and add titles and labels to it. So we'll start by making a figure, which is the area that contains the plot, and an ax, which is the plot itself, using PLT subplots, for example, to which we'll just pass a fig size, and we'll give it a fig size of 6 by 16. Then on that ax, which is this area that I'm now going to use to plot, I will now plot L and Q as I was before. So if I do that, you see now that I have the same plot, but it's simply bigger. Nothing else has changed. So let's build this up. I'm going to add a grid. So that's my grid. We'll add a title and then some labels. So set title, and here we'll say that the flow rate, which is going to be in meters cubed per hour, versus plug length in meters. We can set a font size for this text. So we'll say font size is equal to 16 to make it a little larger than the labels. And then I'm going to set, similarly as I did for the title, text for both the X label and the Y label. So let's start with the X label. And so on X, I'm going to have plug length in meters, and I'll set a font size for this of 14. And I'll copy this line simply so I don't type too much, and then change this not to the X but to the Y label. I'll keep the same font size, but of course now I want this to be flow rate in meters cubed per hour. Once I've done this, I'm going to call plt.show to show my plot. So we now have 7 lines of code and an image that hopefully speaks better than the previous one that we had. Now we can take this a little further, and I'm going to show you now some code that is already in the notebook, just simply so I don't type all of this out. But to show you how we can take this plot, these lines of code, put them in a function, and then add some interactivity to them. And so what I'm going to do is I will now delete these superfluous cells and run this cell that I've written before and just step through it. I'll demo it first, and then I'll explain what's going on in the code. So we have the same plot we had before, but as you see, we now have a little widget at the top. And if we move this widget, we're actually changing the pressure differential across our sample. You notice that the label top right is updating as we go, and the curve is being recalculated. So as you'd expect, as we go to a dp of 0, flow rate also drops to 0. Okay, so a nice little widget that we have inside of these Jupyter notebooks that allows us to explore the parameter space of our functions interactively. So how do we do this? Well, it's not much more code than you've already seen. So let's start with line 7. Line 7 was the function that we defined previously, multiplied by 3,600 as we did before, and then returning Q. So we're calculating this flow rate. We're doing that using values that we'd already defined. So purists would tell us that this is not the nicest way to do it, but for this demo, we're using values that come from outside of this function. We're then making the plot, and this is the same thing as you've just seen. The only addition is an addition on line 16 of the text. And we've also limited the Y value so that it doesn't scale as we recalculate the flow rate. So everything inside here is essentially what you've already seen in this short demo. Now, what's new is that we are importing this interact decorator. So from IPY widgets, we're importing interact. And what interact allows us to do is, on top of a function, it allows us to add this decorator. And what a decorator does essentially is a wrapper around a function that will provide additional functionality to that function, if I may say so. And so what we're doing here is we are passing dp into our make plot with dp, so the pressure differential. And what we're saying is we say we want to go from 0 to 4 megapascals in steps of 0.1. And so here you see that I go indeed from 0 up in steps of 0.1 all the way to 4. Now, in Python, there are many ways to make much more complex data visualizations, 3D visualizations, interactive visualizations. But I find that IPY widgets and Interact are an extremely useful tool to simply explore parameter space of your data with very few lines of code. Okay, so now that we've taken Darcy's law, put it into Python, turned it into a function, into a plot on multiple data, and finally into an interactive plot where we're changing or exploring both plug length and DP. And I want to turn my attention to a slightly different field. So actually, Martin is telling me that when I was moving this, the plot was off the screen. So let me just show that again. As I move this slider, my plot is updating on the fly. And by the way, I hope you're not hearing the Slack notifications that I'm getting. Hopefully, if you are, it's not too disturbing. So I'm now going to turn my attention to a different area. We're now going to go to an area of structural geology. We're going to look at the Ramberg-Biot Equation. So this relationship is really looking at folding of layers enclosed in a matrix of different viscosity. And so for the same viscosity of the enclosed layer, as the enclosing viscosity changes, the dominant wavelength of the fold in the enclosed layer will change. Now that might sound a little abstract, so I've copied a link here to this blog on the AGU, and this behavior is what I'm talking about. So you see this quartz layer being folded through both a sandstone and a shale. The shale has got much lower viscosity, and so in there, the dominant wavelength of the quartz is much shorter. Now, obviously, this is a small-scale example, but it nicely explains, I think, visually what we're talking about. So let me go back to the code now. So this code I won't explain. It's simply to generate this plot and to try and explain why I'm doing this and how, well, what the motivation is behind this. So first of all, in the notebook, there's a link to the Google Map source for this location. This is northeastern Kurdistan in Iraq, so just south of Amedi. I don't know if we have any Kurds or Iraqis out there, but this is an absolutely beautiful part of the world, which has had its fair share of turmoils, but certainly a much nicer place nowadays. I was fortunate enough to do a lot of field work in this area with a lot of Kurdish people, and this structure, the Gara anticline, was one that we were interested in when I was working in Kurdistan a few years back. So the question was, we have this large-scale structure, and this structure is Cretaceous. So let's say we've got this large-scale anticline at the surface in the Cretaceous. And then in the core, and you see it more on the topography map down here than in the satellite image, but in the core, over here in the east, we had Jurassic rocks exposed. And so using Ramberg-Biot on first principles, given the different viscosities of these rocks, we may have expected to drill at the crest in the Cretaceous, but actually hit a syncline in the Jurassic. And so I'm going to show you how we reach this. Obviously, these are just sine waves, but I'll show you how we can look at real data from this area and try and get an estimate for this behavior. And I can tell you already, we did go and map this area, and indeed we did find two crests of anticlines in the Jurassic down in the southeast of the Gara structure. And therefore, at the Jurassic level, had we drilled the crest of the Cretaceous structure, we would have indeed been in a syncline. So first principle, basic equations that translate really well to fieldwork. So the first exercise here obviously is to take the equation that I just listed above and to turn it into a Python function. So you can't see it on screen anymore, so I will define this function, and as before, I'm getting some notifications from my host and colleagues. So let me just see. Yes, so a couple of things. First of all, I'm going to turn the volume down on my machine, so hopefully you will not be disturbed too much. I can't see my volume, but hopefully that's turned down. Hopefully you won't be disturbed too much by the Slack notifications. And I might slow down on the coding parts. I think perhaps I'm going a little fast. Now, of course, if you're watching this live, I'm afraid you just have to put up with that. If you're watching this in the future, do pause the live stream, right? So that you can catch up with what I'm doing and hopefully actually code ahead of me rather than behind me. I'm getting a lot of notifications on Slack, so I do apologize if I look a bit distracted occasionally. It's difficult to focus on two things like this. Okay, so I'm now going to try to code up this Ramberg-Biot equation, but in Python. And so let's call it Ramberg-Biot. And so this will take T, the thickness of the layer, nu and nu0, which are the viscosities of the layer and enclosing layer, and nothing else. As before, I'm going to copy a docstring from over on my other screen so that I don't have to type all of this out. I didn't actually say before, but it's really important in Python to realize that white space is crucial. And so what I mean by white space is these four spaces, this indentation. White space and indentation in Python are essentially what define the structure of the code. And so again, this demo is not about teaching you that, but it might just be worth mentioning. So we now have in our function the input values that we're going to need, T, nu, and nu0. And so we can now calculate L, so the dominant wavelength, using the relationship from Ramberg-Biot. So this was 2 times pi. And so for pi, I'm going to use pi as a constant from numpy. So I'm not going to write out 3.14, etc. This was multiplied by T, the thickness of the layer, multiplied by, in brackets, the viscosity of the folded layer, divided by 6 times the viscosity of the enclosing layer, so nu0. And all this to the power of 1 over 3 to the power of a third. So the Ramberg-Biot equation tells us that the dominant wavelength is going to be 2 times pi times T times nu over 6 times nu0, so viscosity of folded layer over 6 times the viscosity of the enclosing layer to the power of a third. And I can now return L. So as before, I'm not seeing anything immediately after this. However, if I add a new cell with the A key as a shortcut to add new cell above, and if I try to auto-complete Ramberg-Biot, I now have it. And if I shift tab, I now have access to that docstring that I pasted in, that I added to my function. So I'm going to leave this on screen just a second while I talk about the next step. So hopefully the purpose of using this Ramberg-Biot equation was clear. So remember, what we're looking at is a stratigraphic sequence, different mechanical properties in the rocks, so different mechanical stratigraphy and different thicknesses. And what we're interested in is, on first principles, as a really simple approximation, given a surface structure, would we expect the same number of crests as we drill down through the sequence? And so what I have here is some input data for Cretaceous, Jurassic, and some Triassic formations in Iraqi Kurdistan. And the thicknesses I have there are taken from the wells we had at the time when I was doing this work. The viscosities are just estimates. So we're really just looking at relative values of viscosity for different layers. So these are by no means measured or even accurate. And we're really just looking for first order estimate of what might be going on, really as a function of thickness. So before I can really use this, I'm going to have to introduce two Python types to you that we're going to use. And I want to say straight away, if you're new to Python, what I'm going to do now might go over your head, or it might be too quick, I should say. Please don't worry about that. What I'm really interested in showing you is that, again, with relatively few lines of code, we can explore some data and get some plots out and trying to understand the geology that we're interested in. That's really all that I'm trying to show. So if you can follow what I'm doing now, that's great. If you're watching in the future, of course, you can pause, come back, and try it for yourself. So what we're going to do, or what we'd like to do, is print the results of the calculation of this Ramberg-Biot calculation for each row in this table, right? But before we do that, there are different ways of doing this, of course, but before we do that, we need to store those data into different structures. So what I'm going to do is I'm going to put the values, so 7, 13, 19, 17, 80, 17, 19, and so on, into a structure called a tuple or a tuple. And this will allow me, inside of that tuple, to index into them and retrieve one item at a time, which I'll be using for my function. But then I'll put all of these values into a great big value, a great big object called a dictionary. And a dictionary is essentially a mapping of keys to values. So the keys, excuse me, the keys will be the formation names, and the values will be these tuples of thickness nu and nu0. So again, this might sound somewhat abstract, and if it is, right now I would say, please don't worry about it. Maybe just sit back, watch it happen, and when we get to the plot, you'll see the use of this. If you can follow, that's great, of course. So first of all, let me add a few cells here, once again, so we don't get distracted by what's below. Oops. So I'm using the key A to add some cells above where I am. And I'm now going to make a tuple. And an example we very often use is I'll say I have coordinates. And so my coordinates might be 1, 2, 3, 4, 5, 6, minus 999. So X, Y, Z. So those are my coordinates. Now, I can actually go into that. Python, I haven't said, is 0 index. So I can go into that and say, inside of this object, these coordinates give me back only one value. And so, for example, if I want the first value, that would be coords 0. And if I want the last value in this tuple of length 3, that would be coords 2. So that's great, but you'll see what we're going to do next is we're actually going to take these tuples and we're going to extract X, Y, Z from them in a single line. So we do this with what's called simultaneous assignment or unpacking. And so if I say X, Y, Z equals coords, I now have access to X, to Y, and if I scroll up, to Z. So again, this might sound a little fast at the moment. I realize you've not seen, if you're new to Python, you've not seen much Python yet. But what's important is that we're simply storing data inside a structure that might be useful for us, right? So I've decided to store these properties, so thickness nu and nu0, inside a tuple, just like coords. And I'll later be able to extract those values by doing this trick where I say X, Y, Z equals coords. And what I'll probably do is I'll do something like T, nu, nu 0 equals my data tuple. Now this won't work, so I'm going to comment it out, but just so that you see what we're going to do later. Okay, so this is how we're going to store the values. And now remember I said I would store those values together with their labels, so the stratigraphic formation, inside of a dictionary. And so the way we do that is I'm going to make my dictionary. And so my dictionary takes curly brackets, and I can have a key, for example, key 0, that corresponds to a value. It could be anything. So here it's just text. And I could have key 1, which corresponds to another value, say 43, for example. And unlike the tuples, so let me execute that cell. Unlike the tuples, we do not access dictionaries by index. We access them by keys. So if I look at my dictionary and ask for key 1, for example, I get back the value 43. Now, of course, this value 43 could itself be a tuple, and then I would be returning a tuple. So that was the setup for what I'm going to show you here. So here what I have is data is now my dictionary. Notice the same pattern as we've just seen in my dictionary here. So curly brackets, keys, and values. The keys are the names of the formations, and the values are these tuples. So 3 numbers separated by a comma. So if I execute this cell, I now have access. If I look at data here, I have access to those data. So as we were saying before, we could print this out. So I could make, for example, a print statement where I say formation, and then I use a \t to add a tab character and say wavelength. And so this will print at the top when I run this cell. And then I could use a loop. And again, this might sound a little strange, but we're doing exactly what I just showed you before. So what I'm saying is for formation and inputs in my data.items. And again, I realize this might sound like some too much jargon, but what I'm doing is data is this dictionary, and data.items, actually, let me show you that. Data.items is this object that contains these tuples, right? So they have the formation name and then the value, so the key value pairs. And so when I say data.items, that's a tuple, and I can extract that into formation and inputs exactly like I extracted XYZ from coords. So that's the first step. The second step is I'm now going to extract from items, which is this, the thickness new and new 0. So now I will say T new and new 0 is equal to inputs. And at this point, I've got everything I need to calculate the Ramberg-Biot equation, or the result, the wavelength, using the Ramberg-Biot equation. So if I say, for example, RB, I'm going to use that as the stored value for the Ramberg-Biot calculation. I want to use this equation, and I want to pass in T, capital T for thickness, new and new 0 that I've just gotten out from my inputs. And I can now print these out. So for example, I could say, I want to print the formation and I want to print the value. So I could start by doing formation that I have and RB, for example. And if I print that out, you see that I get my formation names, a space, and then the value with obviously a lot of decimal points. So Python allows us to change this or to format this slightly or more in a nicer way that's more legible. And so to do that, what I'll do is I will put both of these properties, or these values, I should say, inside what's called an F string. So let me illustrate. So first of all, I put this in a string. If I run this, I just get formation RB, nothing fancy there. If I add an F in front of this, there's no change immediately, but what's going on now is this is an F string, and that means it will accept inside of curly brackets Python code, and it will evaluate that code before printing. So now what I'm doing is I'm back where I started. I'm simply printing the formation name and its value. But inside an F string, I can add other things too. So let's add, for example, colon, \T for a tab character. So this is starting to look nicer. And all these decimal points at the end, I don't want to show all of those. So let's get rid of these. And for that, inside an F string, there's a mini formatting language that we can use, where I can say I actually want no decimal points at all. And perhaps I want a unit, so this is in meters. Now, you see here that I've got different lengths of keys, and so a single tab character isn't necessarily enough. For now, I'm going to leave that, but we could obviously clean this up. Now, this is all fine, but here we're not saving the data anywhere. And when you're doing this kind of analysis, very often you're obviously going to want to save it to Excel, to a CSV, to some structure outside of Python. And so Python allows us to do that relatively easily as well. Oops. So let me delete these cells. And so what we're doing here, there's a lot going on this cell, so I'm going to dwell on it for a bit. I've run it and you haven't seen any output, but we can look at that in a second. So first things first, we're importing CSV, just like we imported NumPy or Matplotlib, and CSV is part of the standard library in Python. What I'm then doing is I'm building up a dictionary similar to what I was doing before. So this code is essentially the same as the code I just had. What I want is to have a dictionary with the wavelength names, so the formation names and the values. And then I'm using this context manager. I apologize for all this jargon. What this context manager allows me to do is to first open a file with the open function. I'm opening that file in read mode, in write mode, so I can write into it. I'm then passing a relative path, and so inside of this folder, I'm going to the data folder, and then I'm writing a new file called wavelengths.csv. And then with the CSV library, I will write into that, that CSV file row by row. So what we can then do, I'm going to quickly switch over to my home notebook. And where did I go? I went into data and I saved the CSV wavelengths.csv. And you see now that I have these data saved out in a text file that I can then use, import into Excel or anywhere else I might want. So again, I don't want you to get stuck on the details of the syntax here. All I'm interested in showing you is really the fact that we can both read and write CSVs directly from Python. And obviously those are very, very common in the scientific world. Now, this demo is way too short for me to introduce pandas to you, but it would have been incomplete without at least using it once. So what pandas is a library that is built upon NumPy and allows you to handle tabular data, 2D tabular data extremely efficiently. So what I mean by tabular data are typically CSV files or Excel files or a whole slew of other files that you can find in the pandas.read methods. And so here what we're doing is we're reading the very file that we've just created, and I'm saying that I want to use the names formation and wavelength as my index and my data column. And again, please don't worry about the syntax here too much. What we're interested in seeing, okay, with a few lines of Python, we can achieve these results. So I now have a new object in my notebook called df_wave. And so when I look at this small object, I get this nicely formatted HTML table where I see my formation names in the index and the wavelength column is the values. Now these values are represented with the full precision, of course. When I was plotting or printing them before, I was simply formatting them, but I wasn't truncating them. So we've calculated these values and we've now wrangled them into different data structures. I wanted to show you tuples and dictionaries because they are very common. But in this kind of context, a pandas data frame is probably much, much easier to use. So we can now plot the results. So with one line of code, I can make a plot that's valid, but I'm sure you'll agree it's not very legible. So all I'm doing here is I'm using plt.bar, so I can make bar charts in matplotlib. I'm passing the index as x and the wavelengths as y. So the index is going to be all these formation names, and the y are going to be all the values. I'm sure you'll agree that we should make this look a bit better. So the first thing we're going to do to dress up the plot is to make a list of colors, and we'll use the colors for Cretaceous, Jurassic, Upper Triassic, Middle Triassic, and Lower Triassic. So I'm just putting these hex codes in there. There's a link to the hex color code, or to a hex color code resource there as well, if you're not sure what those are. These are just colors, just like you could represent them in RGB values, we're representing them with these codes. So I now have access to this list, this container of colors, and I'll be able to use that in my plot. So again, I didn't want you to watch me type all this out. So let me run that first and then explain what's going on. So hopefully you'll agree that this plot looks nicer, I hope, than the one I had before. And so what I'm doing here is I'm making a figure and selecting a figure size, so somewhat different to what I was doing before with my fig, ax. And then inside that figure, I'm using plt.bar, and the first two lines here are the same that I had just a second ago with my really ugly plot. And so then what I'm doing is I'm setting colors. I'm changing the Z order, so where the plot is being displayed relative to the grid that comes after. The width of the bars as well. I'm setting a title, a font size as before, Y label, so this is this label here. The X ticks, I'm just making sure that I have a tick for each bar with the correct label. And then I'm adding a grid. I only want the y-axis on my grid, and the z order or z order here means that that is being shown behind my bars, not in front. So again, just under 15 lines of code, and you can now take these data and hopefully appreciate what I was doing relative to the map I showed you right at the beginning. So I don't want to scroll up and down in the notebook. I think that's usually very confusing. But if you remember the map I had initially, we had a large scale macro structure, and the cliffs there were formed by Cretaceous, Acrobecme, Cometan, Kamchuka rocks, Cretaceous rocks in northern Kurdistan. And the core was Jurassic. And so there we were looking at now Kelekan, Sargelu, Sekanyan, and again, Jurassic rocks from northern Kurdistan. And so on first principles, with all the usual caveats about the data that I've put in there, you see that before going to the field, I already had an inkling that we might not have the same wavelength in the Jurassic as we observed in the Cretaceous. And so indeed, going into the field, that is what we found. Okay, so hopefully I've not lost anyone. I don't know what's going on YouTube or actually on the Slack channel. So I hope people are finding this useful both today and in the future, and that it will encourage you to use Python to practice your geoscience. Okay, now I'm looking at my watch as well. I'm not keeping track of time that well, so I hope my host will be able to point or tell me when we're about halfway through, and then based on that, I will take a break at a proper place in the code. Okay, so moving on, I now want to introduce to you, or move out of the fluid flow and structural geology world. And we'll take I've just been told we're taking a break in about 10 minutes, so that's perfect. So I want to move out of the fluid flow and structural geology world and go into a world that I'm definitely less familiar with, but I've touched upon a lot in my career, and that is geophysics. Now, so far we've been taking equations from Wikipedia or from textbooks that we have behind us and writing them in Python. Now that's fantastic, but Bruges has done a lot of that lifting for you already. So Bruges stands for Bag of Really Useful Geophysical Equations and stuff. And as I alluded to in the introduction, I believe there's a project right now on Transform 2020 where people are trying to add the equations from Mark Zobach's book on reservoir geomechanics into Bruges. So Bruges is going to, hopefully in the coming weeks, become even more useful. So right now, if I import Bruges and use the dir command to list out everything that's inside Bruges, I get stuff that might look a bit weird. And so these double underscore methods or attributes, we can think of as private methods of the library, but I don't like saying private because you can access them too, but we won't focus on them in this demo. What I want to show you is the fact you have a bunch of attributes, some filters, some petrophysics, some reflections, some rock physics things. You'll hopefully soon have a module in there for geomechanics. And so, for example, if you wanted to make a Ricker wavelet, well, Bruges has you covered. So how would we approach that? As before, I'm going to add a few cells here so we don't get distracted by what I have below. And we'll start from scratch. So we'll start with Bruges, if I can type. Looks like I'm getting close to needing a break indeed. So Bruges, and because I've imported it with .tab in a Jupyter notebook, I can get a list of all the available modules or attributes or functions that are available there. I want the Ricker wavelet, so that's going to be under the filters. And again, if I do .tab here, I see that the guys at Bruges have given me access to a whole bunch of different wavelets. I want the Ricker one. And so hopefully you remember now that with Shift-Tab in a Jupyter notebook, I can actually look at the documentation for Bruges, from Bruges and for the Ricker wavelet. So let's hit Shift-Tab 4 times so that I can see the documentation at the bottom of my screen. And this is the kind of documentation I was talking about that's really well written. So first of all, we have what this is. So Mexican hat wavelet. It tells us the actual math that's being modeled. So again, very clearly, we know what's going on. It tells us we can pass a 1D array of frequencies. Now, this is analogous to what we were doing when we were looking at Darcy flow and passing an array of core lengths. So you can pass not just a single value, but multiple values. And then you get your wavelet back. And conveniently, we also have examples of the values that you might typically see in one of these wavelets. So if you're plotting it and you just want to see how it works, you can refer to those. So let's do that. Let's first pass a duration. And I'm going to say the duration is 0.128. We're then going to pass a dt, and we see here the dt is often one of 1,000th, 2,000th, or 4,000th. So I'm going to say 0.001 in this case. Then a frequency. So here I'll say frequency, a frequency, say, of 35. And finally, you see this return t, which is a Boolean. And so by default, if I just go up, by default, it's false. So by default, this does not happen. So what does this do? If true, then the function will return a tuple of wavelet and time basis. And so we're going to set this to true and look at what we get back before we do anything with it. So we'll say return t equals true. And so if I'll close this now so we have space. If I run this, you see that we indeed get back the Ricker wavelet. So we get all of that. And then we get the time array. So I don't know about all of you, but I'm really bad at looking at this and seeing anything out of it. But what we do know from the documentation, if we look at the return statement, is that we get back a wavelet with center frequency f sampled on t. So I can save this as W and T for wavelet and my time samples, and then I can plot this. So plt.plot, and on the x-axis I want T for time and W on the y-axis for the wavelet. And voila, we now have a really nice Ricker wavelet plotted in Python. One line of code. You could then convolve this with your reflection coefficients, and as a geophysicist, I'm sure you could see the value of this. Now, of course, here I've hard-coded values in there, and so hopefully you're already seeing where this might go. We basically, before we were using interact to change values on the fly. And so I've got code written under here, and what I want to do is I'm going to run the code first, show you what it does, and then I will go back and explain it because it is rather long. And so we'll probably finish on this and then take a break. So first, let me run that code and scroll the code away. So here I'm looking at the same wavelet, but you'll notice that I now have some of these sliders and also a toggle button. So I can toggle the fill on and off. I can change the frequency. So I'll try to do this slowly so that we don't get too much lag. And so you see the effect of increasing the frequency or decreasing it massively on the resulting wavelet. Hopefully you can immediately see the value of this as a teaching aid to students trying to understand the impact of frequency on resolution. Likewise, the duration of the wavelet, and here we're going to rapidly see that we can break the wavelet down depending how far we go. So duration decreasing or increasing. And the DT, and here we will really see the code or the wavelet breaking down. I'm not a geophysicist, but I'm sure the acquisition guys will tell you that it's important that they tune their duration, frequency, and parameters so that they get a nice clean wavelet in their data. So I'm just looking at my clock again. So I'm going to explain this code or try to explain this code, and then we'll take a break. So if you're getting ready to stretch your legs, we're almost there. There are 50 lines of code, but please don't run away. By now, hopefully, you should be able to follow a lot of it. I'm not going to go top down. I'm going to try to break it apart into bits that we've already seen. So first of all, the definition line here, line 17. We're plotting Ricker, so that's the name I've chosen. We need to have duration, dt, and frequency. Those are the inputs that Bruges requires. And remember, I had that toggle button for filled or not filled. So I need to pass that in as well as an argument. Then I have my documentation or my doc string. So somewhat different to what I've been having before. I'm trying to build these up as I go. Then this line is the line we saw right above, right? There's nothing different here. I'm calculating W and T using Bruges filters Ricker. And I'm now, instead of hard coding the values, I'm passing them inside the function. And we're going to see how we generate those in a second. We then create the plot. So again, nothing too different here to what we've seen. I'm making the plot. I'm using figax again. Perhaps I should have not done that to be more consistent. There are different ways of creating plots in Matplotlib. So I'm creating a plot. I'm then defining my parameters for the fill between, so for that fill, so that it doesn't go below negative or below 0 into negative. Then I have an if statement, and we've seen these very briefly at the top, but I'm sure you can conceptually understand. We're saying if, in this case, filled, so filled is going to be a Boolean, either true or false. So if that Boolean name is true, we will then do this. And so that means we will fill between x and 0 for the wavelet, where the wavelet is greater than 0. Color equals k means that the color is black. We could change that. So at this point, I have my plot. and all it needs is data to come into the plot. And so I'll scroll up now, and this might look like a lot, but please realize it's definitely not as complicated as you might think. First of all, so we're importing from IP widgets, we're importing these widgets, and what those widgets are the float sliders, the int slider, the checkbox that we've seen. So they're essentially JavaScript objects that we have access to inside of Python. And I also want to say here, I didn't write this out line or letter by letter. I copied a lot of this from the documentation and then just put in the values that I wanted. So the value that I start with, the minimum, the maximum, the step, the description. Continuous update equals false simply means that I don't want it to jump as I'm moving the slider across. And then the readout format is so that I have the right number of the right number of values after the decimal point. So again, remember what I said in the introduction. I'm not trying to teach you this. I'm trying to show you that with relatively short code and code that you can copy paste from different places and adapt to your needs, you can then generate a plot, which I hope you'll see can be really useful to teach concepts or to understand concepts, whether you're a student or an experienced professional. Now, I'm going to take a break at this point. The aim will be to take a 10 or 15-minute break. So there will be a placeholder telling you we're on a break time coming up in a few seconds or a few minutes. And then shortly before we resume, there'll be another placeholder telling you we're about to start again. So let's say 15 minutes break. So I've got 20 past. So let's say 35 minutes past the hour. I will start again. Okay, welcome back, everybody. I hope you are all able to stretch your legs wherever you are. I realize you might be in different time zones, different countries, and so on and so forth. So I do hope you were able to step away from your computer. It was pointed out to me during the break that in YouTube, you are able to pause the live stream and then come back to it, as it were. So that means if you want to have a go at the exercises, by all means, pause that. And then you'll be able to come back to it. I'm just turning my volume down again so that you don't hear notifications. Another thing that was brought to my attention is some people were asking whether this notebook that I'm working in right now will be made available to you. And the answer is yes, absolutely. So first of all, there's a link, or there should be a link pinned in the channel for this talk or this tutorial / demo with the repo. And that includes both the master notebook, if you will, that I started with, and this notebook that I'm working on now. But I will upload this notebook however far I get, and it might be somewhat different to the master notebook as I'm doing some of it live. If you have any other questions, please post them in the Slack channel, and Martin will be right on it, I'm sure. So here we go, moving on. So let's recap quickly. We've looked at fluid flow. We've looked at structural geology. We've now looked at introductory geophysics. I won't go beyond there. So now let's take a DEM, so a digital elevation model, and make maps and cross sections. So we're going to look at a digital elevation map of Mount St. Helens after the 1980s eruptions. After the 1980 eruption, there was only one, and to see the crater left by the eruption. And so we're going to plot some cross sections through the mountain to compare topography pre and post eruption as well. So the first thing we'll do is we will load some data. And so we have these NumPy arrays. So .npy is a file type that comes from NumPy and allows you to store data in binary form so it doesn't take up too much space. And you can load it very easily with NumPy, obviously, as it's a NumPy object. So what do we get back? Well, first of all, we get back a NumPy array, or NumPy ND array, which stands for n-dimensional array. And I just want to show you the shape. So this is the dimensions, or the length of each dimension of each one of these objects. So before.shape and after.shape, and you'll see these are the same shape. And that's important because what we want to do now is we actually want to make a difference map. So if you cast your mind back to when I was showing you loops, just before I introduced NumPy arrays, if I wanted to make a difference between before and after, I would have to loop through basically both of these arrays and try and get the right index in X and Y every time. Maybe I should just show you what before looks like so you can follow what I'm saying. So before is this data set. It has more than 6 values in one dimension. The ellipsis in the middle, these 3 dots, that's basically excluding all the middle, and you're just seeing the first 3 and last 3 columns and the first 3 and last 3 rows. And so this is a 2-dimensional grid of elevations. So at a given XY position in the grid, which are not coordinates, they're just indices, we have an elevation. So we have before, we have after. We can therefore take a difference map. I'm just then setting some parameters that I don't want to rewrite every time. So a font size, line width, you'll see why in a second. And then east-west section 1 and northwest section 1, those are basically indices, and it'll become clearer what those are in a second. Now, there are just over 25 lines of code here. As before, I'm going to run the code first, show the output, we'll discuss it, and then I'll come back to the code and break it down. So here on the left, we see in blue, green, and yellow, we see Mount St. Helens after the eruption. No doubt you can see the crater. And then in blue and red, we see these 2 cross sections. And so these indices, 150 and 200 and 190 or whatever they were, are the indices through which we are slicing this, this array. And so here on the right, we're plotting, for example, in red, the east-west cross-section before and after the eruption. And then on the north-south section, also before and after the eruption. And you see here that we have 3 plots set out in a regular grid here. So we're not doing too complicated things. Plots with lines on them, with labels of different sizes in some cases, multiple data sets on a single plot. So for instance, here, I'm only plotting the after map, but over here and here, I'm plotting 2 maps, 2 data sets, I should say, sorry, 2 data sets together. And you can control absolutely everything about this display. So now let's quickly look at the code that produces that. And again, don't let this throw you. The first thing we're doing is we're making a figure, right? So we're saying we want a figure. You can think of that as the canvas that you're going to draw onto. Again, we're saying this has a certain figure size, so we select that size. We're then going to add these axes objects, and you see that at line 2, line 11, and line 19. And so what those are essentially the plots. Each individual plot in matplotlib is called an ax. And then the pattern is repeated essentially on most of them. We're setting a title. We're showing some data. So on the first one, we're showing a map with imshow, which is image show. So it allows you to show a 2D grid of data. So if we look at the documentation, X is array-like or a pill image. So that's the image data. We're then adding H line and V line here. So that's the blue and red line. We're setting some labels and adding a grid. And so you see, as I move forward, it's essentially the same pattern. I generate a figure, an ax, so a plot area. I set a title. I decide what I'm going to plot in there. So on this one, I'm plotting before and after. add some labels, add a grid. Same thing 3 times. I want to thank Evan Bianco for this. This is his code that I modified slightly. He's a colleague of mine who's a real matplotlib wizard. Okay, so hopefully that gives you some incentive to try and dig around in matplotlib a little bit. I should say at this point that you rarely start writing matplotlib code from scratch. The thing to do is to go to the matplotlib gallery and find some plots that look similar to what you're trying to achieve. Excuse me, and then inside of that, that code, replace the dummy data with your data, and then just change line by line small things one at a time until you get the result that you wish. Okay, so now we're going to move from these DEMs and matplotlib and start looking at well logs. So you see we're really hopefully taking a nice tour through the geosciences, and there'll be something for almost everyone. So the first thing I want to do is I want to check what data I have available to me. So to me, this demo would be incomplete without glob. So we import glob, and then we will use glob. And first I will just show you how we use it. So what does glob do? We can pass a path to glob, and it will return to us a list of path names, or file paths, if you will, that match that pattern. And so I can say, for example, in this current folder I'm working in, let's go into the subfolder called data, and then let's look at all the files with the name something dot, and then I want all the LAS files. However, I don't know how LAS is going to be spelled, uppercase, lowercase. So here I can use a little bit of regex, and I'm definitely not going to talk about regex here, but it allows us to basically match patterns of text. And so what I'm saying is I want to have any well that starts, or that has a, sorry, any file that has an extension LAS upper or lowercase. And so you see that glob.glob allows me to search through my operating system and gives me access to essentially my whole hard drive or connected drives, and returns to me a path. Now, why is that important? Well, we can now access the data thanks to that path. So first I'm going to save this list as wells. So I now have a list of wells that I can work with. And now I'm going to use the library that I mentioned in the introduction called Welly. And Welly is built upon, or depends, I should say, upon LAS.io. So LAS.io handles the input-output of the LAS files that we're looking at here. But Welly provides us with additional functionality and objects on those LAS file objects. So let's meet Welly. So from Welly, we will import for now just the well object. So we don't want to import the whole library yet. Well, actually, we won't import the whole library. And depending on time, I might have to skip some of this, but I wanted to say straight away, there's a link to Welly in this notebook to the GitHub repository, and it's well documented. There are tutorials there. So if you find that you're working with Welly, definitely check that out. There's actually on the Software Underground, there's a hashtag Welly channel as well. So you'll get help from the devs and from users really quickly if you're looking for some help on Welly. Okay, so I'm going to import the well object from Welly. And now what I want to do is read one of these LAS files, save that in Python as an object I can then use. And to do this, we have a slightly different construct to what we've seen so far. I'm going to use that object, that well object, and that has a constructor where I can say from a LAS file, create a well object. And that well object will then have some attributes and properties attached to it. So it will be able to do things like plot itself or other things we'll discover together. So I want to go into that same data folder, and I'm going to take, I don't know, the R39 well, for example. Now I actually want to save this into an object, So let's call it well underscore R39. And then I won't have to type that every time. I can autocomplete with tab and then enter. So don't worry if you have a rather long name and you're afraid that it's too long to type. It's much better to have a descriptive name for your variables and use tab to autocomplete rather than to use X, Y, Z that you won't remember what it is later. So, okay, so I've not run this cell yet, but if I run it, three things will happen. First, I will import well, from Welly, so I'll have access to that. Second, I'll make this well object out of that path or that file. And then when I look at that file, Welly will actually return to me a nicely formatted header table, if you will. And so anyone working in subsurface data will probably not be surprised to see that very often you have things that are fields that are not populated or that are populated wrong. This is sadly very common. Anyway, so the first thing we get when we inspect a well is this table. And so we can see quite a bit of information about it. This comes from Nova Scotia, and we have a bunch of logs inside the data field. Excuse me. So let's look first at a single curve. So I'll look at my well. Here we go. So I'll look at my well. So well R39. And then if I look at data, this might look familiar. So this looks a lot like a dictionary. So we have keys, which are the curve names, and values, which are the actual curve arrays. Now we're going to look for starters, let's say at good old GR, good old gamma ray. And so if I look at that, again, I immediately get a small table. And that table gives me some useful information if it's been populated, of course. So the run, what the null value is, service company, and so on, some stats on my log as well. So min, mean, max that I can see over here and see immediately if I've got some weird values. And then the first three and last three values of the log. Now, it's important to say in Welly, each log knows its depth. So you see here, gamma ray has got a depth. And so it's not stored as an object, it's calculated on the fly. And so the depth, as long as for a given log, you know the start depth and the step, you have access to what's called the basis. And so the basis of the log will give us its depth. Now, initially, that was strictly in SI units, but I believe as of this week, there's now a version of Welly where you can actually load, you can have feet for your depth. Okay, so let me show you what I mean by that. So if I save, have I done that? No, I haven't. So I'm going to save this well R39 dot data and then gr into an object I will call gr. And so if I look at gr, I get the same thing we did just a second ago. But what I can do now is I can use a method called toBasis. Excuse me. And I can pass a start and stop to that. So let's say I want to start at 3000 and stop at 3100, for example. And I can then plot that. So inside of Welly, I have access basically to these wrappers for matplotlib. So I don't have to write all the matplotlib code. I can immediately get out a nice curve that looks like a log curve, formatted properly with the correct aspect ratio. And here you see I'm going indeed from 3000 at the top to 3100 at the base. Now, another nice thing you have, I'm not going to show you everything in Welly, there are a lot of things in there, but one thing I really like, and it's in the tutorials, so you'll find that on the GitHub actually, is you can smooth a curve. So if we go back to what we just had, gr to basis, and then pick a start and stop, let's say, I'm going to say start at 2600, and stop at 3000 this time. So again, this is the data that I have. On here, I can use the smooth method, and the smooth method will take a window length. And so in this case, I'm going to say 10 meters. Now to say 10 meters, I have to pass samples equals false. And so if I run this, I now have access, I can save this object, let's say SM for smooth, and I can now make a plot. So as before, figx, and then let's do a PLT subplots. And so just to explain perhaps as I'm going, I've taken this curve, gamma ray, I've selected only an interval from 2600 to 3000. I'm then smoothing it with a window length of 10 meters. And so now what I want to do is I want to plot the original curve and the smoothed curve to show you how we can do both with Welly. So as before, fig size is going to be 2 and 10 so that we've got a long, thin well. And then I'm going to say gr.plot. And so here I have to tell Welly on which axis I want to plot this. So remember, an axis is a single plot inside of my figure, which is the canvas. So here I have to say ax equals ax. And then I also want to plot not gr, but sm exactly the same way. Ax equals ax. And then I'll maybe change the line width here so that it's more visible. And so let me keep the code on screen as well as the output. So you see here that I've got my initial or my input data in blue, and in orange, I should actually say that. I don't know if anyone's colorblind that's watching this. So let's try not to use colors. So the high frequency line is obviously the input data, and then the smoothed curve you can see running through that as a function of this window length. And so just to illustrate, if I change my window length, obviously I'm matching the input curve less and less. And so you might use this to, well, all kinds of reasons in geophysics or actually in petrophysics. Okay. Now, those were a couple of examples of loading a well, a single well, and looking at a single curve in that well. But one thing I found that I really wanted to do when I was working on well data, and I always struggled with, was the following. Sometimes all I want to do was load my well and immediately see all of the logs in that well without having to go through some fancy petrophysical package. And so you can do that in Welly. You can, on the well object, you have access to a plot method, plot function. And so what this does is it literally plots every single log in your well. Now, you might be saying, yeah, okay, but I've got all this white space above me, so let's try and fix that. So the first thing we might do is, remember we have gamma ray, so I'm just going to look at gamma ray so I get the depth range, for instance. That'll be the same across the wells. And so now inside of my plot, I can actually pass extents. So let's go back to our well R39, do the same plot as we were doing before, but then pass extents in there. And I can say, for example, from 2000 to 3500, so that I'm enclosing the depth range of my well. Okay. So again, one line of code, and I can immediately see if I've got some weird values in one of my log, if I've got some trends that I might want to look at, what logs are available to me, and so on. And so doing this in one well is great. Being able to do it in a group of wells, I personally think is even better. So let's say for well in wells, and just as a reminder, what is wells? It's this list of wells, and so we can iterate over that list. And so here I could say that W is going to be equal to well from las. And so here I'm going to pass in each time one of these paths. And so I'll say this is well. And then I can do w.plot. Now, in the interest of time, I'm going to say I only want the first 3 wells because my computer isn't that fast. And this will take a short while to plot everything. And again, this is a nice way, I think, to load data up and very rapidly see what's available to you in terms of data quality and data availability, of course. So there you go. We have the first 3 wells in that list, all plotted up with 1 line and very short wait. Okay. So I now want to show you another thing. So a well in Welly also has a data frame object. So we've seen a data frame briefly before. And again, we're not trying to teach you all of this, but just to illustrate some of what we have. And so if I take my same good old R39 well, I can get a data frame out of that. And so that is all the data in that well, each curve, all the data. And you notice that the index we have is the depth immediately. So we have 7,800 rows, 20-something columns. And data frames afford us a lot of tools in order to inspect our data. So this isn't really the place to do that, but I do just want to show you the describe method. Oops, if I have a typo, I'm actually quite happy. That's the first error you've seen in this live coding session, so that's not bad going. So the describe method essentially summarizes our data immediately. And so here you see that again, for each curve, we have the count of the points we have. If these counts are different, that would mean that we have some null values or non-existing values. We then get some statistics. So we can very rapidly inspect the data and see if we've got strange things. So another useful method on here, or attribute I should say, on the data frame is we can get out a reading of all the columns that are available. So here there are 22, and of course you can scroll over, but if you had many, many more, you wouldn't want to do that. So again, my R39 well, my data frame, and then the columns attribute. And that will return to me a list, if you like, or something like a list, a container, I should say, of all the columns in this object, in this well. So if we take, let's say, a couple of these columns, we could actually get some statistics just for those using the method we had above. So how would we do that? Well, I would do my well 39. I'm going to add a few cells below here, so this is closer to the middle of my screen. So well R39. Then I'm going to turn that into a data frame as we did. And then we can use this lock method where I say I want, for example, all the rows, but then I only want, let's say, the gamma ray and row B, if I have row B. I've got row B. So if I run this, I get a data frame going from start to end. I might say, actually, I don't want the whole thing, but for now we'll leave that. And I can then describe this. So I now have the stats only on those two columns, or those 2 logs, I should say. One thing that I often show is you can actually pass percentiles in here. Percentiles, and so if we wanted not 25, 50, and 75, we could say we wanted P10, P50, P90. Obviously on gamma ray and row B that might not be too pertinent, but just to show you what you can do. So you've now seen loading a well, doing a quick visual check of what the curves are, how to load a single one, how to visualize several at a time. So now let me show you how you can use Welly to QC your data. And so let me run this and then explain it. So Welly gives us access to this QC object. And so what you can do is you can build up a dictionary of tests, so a mini data set of tests that you want to run. And so you can say, for example, for each for each column, each curve, I want to run these two tests. So I want to check that there are no gaps. I want to check that it's not monotonically increasing. For the gamma ray, let's say, I just want to check that everything's positive. Now, of course, you might have different checks. And for row B, also all positive. We then run this code with .qctable.html, passing our test lists, and we can then plot that with the HTML package, the HTML module that we get from IPython display to get a nice HTML table. And so hopefully you see that this could be useful if you were setting, well, I can see at least two immediately important applications for this. One of them is machine learning, and I believe that's why this was built. So trying to see if all your logs are valid and if you can use them in your machine learning exercise. And the other one that I probably have dealt more with is simply data rooms. So you go to a data room and you want to actually check that the data you have is valid. Well, this is going to be super quick in order to do that. Now, what if you want to plot not a single curve, but you want to actually plot several curves for one well, so make a comp log, if we will? Well, then we have strip log inside of the same, well, we've got strip log thanks to Welly. It's a separate package that we get with it. And strip log will allow us to build up a legend and then have different display parameters for each curve. So here we're basically just setting that up. We're building that up where we're saying, okay, we want to have these tracks only. You notice that here I've got 3 tracks in the same column, 3 logs in the same track, I should say. We're using a built-in legend for the color. So this is the Nova Scotia Department of Energy. And then what we're saying is for each curve, we want a color, a line width, a line style, X limbs. So what are the limits on there? The X scale and the curve mnemonic. And so you could actually have set up some aliases as well so that you take multiple gamma rays and plot them all just with gamma ray. We then use this multi-line string that we've developed, that we've written here, and save that as a curve legend, so from strip log. And we now have this complete legend. So what can we do with this? Well, let me scroll up a bit and again try to put this in the middle of the screen. So well R39 dot plot. You hopefully remember this. This plots the whole thing, but this time what we're going to do is we're not going to plot the whole thing. We're going to say that tracks is going to be the track list that we just made up here. So this track list. And then we're going to say that the legend that we want is the complete legend that we've just built here. And then as before, we'll pass extents. So in this well, let's say as before from 2600, and I need to pass this as a tuple from 2600 to 3000. And there we have it. We have obviously one line. We could make this even nicer, have fills, have well tops and all sorts of additional information. But I really just wanted to show you as a demo of something you can do that again with a single line of code. And there's a bit of preparation above if I'm fully genuine. There's obviously all of that. But we can build this comp log of this ExxonMobil et al. 3 well from Nova Scotia. Okay, and we're actually getting close to the end of this demo. And so that I think will be good on time. It also allows me to tell you that once I've finished this demo, I'll probably, well, I will, if I've got time left, join the conversation on Swung. And so either answer questions there, or just make myself available if anyone has comments, suggestions, or questions. So moving on, I'm moving out of the well world and we're going to move into the segyio world to wrap up this demo. And so what I want to do is load a seismic volume and inspect slices of that volume, so inlines, crosslines, time slices, using Equinor's segyio library. So you have a definition from the documentation there, and essentially what segyio is built for is the input-output of segyio files for essentially developers rather than, let's say, seismic interpreters. I'm going to load a seismic cube here. Let me run this in case it takes a while. It didn't. I load this seismic cube and you notice that it just worked. Now, I do want to point out, of course, this is a curated seismic cube. It's nice and clean. Anyone who works with real seismic will know all the usual caveats, and I've pointed you here to one of Matt Hall's blogs about the segyio format, which I recommend you read. If you are following this either live or in the future and you don't have the file, there is a link here to download that file from Agile's S3 bucket. So, okay, so we've imported segyio and we're using another of these context managers that opens and then closes when you leave the file that you're reading. We're passing to it a path of the penobscot 0 to 1 second segyio. And then we're opening it with segyio.cube, and we've now saved it in C. But the file is now closed. I could delete that penobscot file off my disk. I have the C object in RAM. So what is C? Well, it's my seismic, but what type is it? It's, again, a NumPy array, right? So an ND array is an n-dimensional array. And so let's have a look at its shape. So that's going to be the length of each dimension. So we can see here that it's a 3-dimensional array of length 601, 481, and 251. And we can assume for now that those are inlines, crosslines, and time slices. So again, you can pause this video now, either if you're watching it live or if you're watching it in future, and try to make a plot at its shape, for example, through an inline. And you'll have to make sure that inlines and crosslines are transposed, and I've given you a link there to the NumPy documentation. Let me show you what I mean by that. So how do we do this? We're going to show just an inline or crossline. So while the data are 3-dimensional, we're going to show just one slice through the cube, and that will be 2-dimensional. And so for that, I can use imshow as we did before. Now, if I try to pass C on its own, that won't work. So remember that C is this multi-dimensional array, 3-dimensional. But in fact, I can index into that, and let's say, for example, take only the first inline in there and all the inlines and time slices. And this would be equivalent to that, where we say in the first dimension, I don't want to say rows and columns, of course, in a 3D cube, but in an n-dimensional data set, you could have even more than 3 dimensions. Anyway, in the first dimension, I want index 150 or index 150. I don't want to use the word slice because that would be a range. We'd go, for example, from 150 to 250. Here, I just want the 150 inline. In the second dimension, I want everything. And in the third dimension, I want everything. And so I can actually pass this. If I show you the shape of this, this is now 2-dimensional. So I can pass this into imshow, and I now see a plot. And hopefully the geoscientists among you will see that the seafloor is subvertical, so there's something wrong here. So the quick fix for that here is to transpose that matrix with the dot T, and we now have a horizontal or subhorizontal seafloor. Now, you probably see that this is quite washed out. So we probably have some amplitudes which are really very high. And so when we're scaling the image, the rest of the data are being washed out. So what we can do is we can actually get a percentile values in there and use that as our amplitude range that we want to look at. So if I do NP, if I can type percentile on my whole cube and I want the 98th percentile, I can then rerun the same code as I had before, imshow of C150 and everything in both other dimensions. I need to transpose that again. But now I'm going to pass some keyword arguments, so some additional arguments into this function to change how it's displaying. So first vmin will be minus ma that we've just calculated, and vmax will be ma. And so if I run that, you see that now indeed we're getting more of the definition of our data. Let's see, yes, I want to copy this so I can select the cell, hit C and then V to paste it below, and then show you, perhaps you don't like this, this color map, so we can change that and say, for example, we want to use grays for structure. And as well as that, I'm going to now look not in an inline, but let's say I want to look at time slice 140. And there you have it. We're slicing through a cube. We can change the color map. Matplotlib has a lot of default color maps that you can access. plt.colormaps will give you a list of those color maps. Each color map has got its equivalent reverse color map if you pass _r to it, or if you add, sorry, _r to the name of the color map, as you see there. I recommend you go and visit choosing the right color map in Matplotlib. It will give you a list. If you search for that, it will give you a list of perceptually uniform color maps that are suitable for people with or without color blindness or different types of color blindness. So make sure that you're not excluding people from your scientific analysis just because you're picking a bad color map. Now, another thing I want to say just as we move forward, and this is going to be the concluding section of this demo, is what I've done here, of course, is relatively quick to do, but I have to rewrite the code every time. And so hopefully now you won't be surprised to see that I'm going to put this in a function and I'm going to add some interactivity. So the first thing I'll do is the file loading. I'll put that in a small, tiny function here. And actually I should have a doc string in here. So load a seismic cube and load a seismic cube. And so this will be, for example, my args or my arguments will be volume path, and it will return a NumPy array. And so all I'm doing here is I'm going to call this function, pass a volume to it. I'm sorry for the scrolling. Call this function, pass a volume to it. That will be given to segyio open. We will save a volume using segyio.cube, and then we will return that volume that we can then use as we need. So again, rather a long function. So let me walk you through it and hopefully you'll be able to follow. So don't look at the whole thing to start with, just line by line. So I'm defining a function and it's called seismic plotter. And that function will take a bunch of arguments because I want to be able to change things on the fly. So I want to be able to change the color map. I want to be able to change the section, the inline, the cross line, or the time slice, and potentially give it a different volume as well, although in this example, we'll just use a single volume. So then we're going to plot a given seismic inline, cross line, or time slice with a choice of color maps. And so the first thing I need is I need my volume, and I'm calling that function that we've just written above. I then have to set up a whole bunch of plotting parameters. And so this is a large dictionary. And let's not look at the whole thing, but for the inline, for example, I'm selecting an amplitude. So I'm selecting a subset of my cube. And then I'm setting some labels, passing some different arguments, changing some colors and so on. I really don't want you to get bogged down in the detail here. I'll show you the result and hopefully you'll see then that you can, if you want, actually reuse this code and modify it for yourself. So the inline, crossline, and time slices all have different settings, if you will, and these are those settings. Then we're doing the same thing as we did just a few minutes ago, scaling the amplitudes in our data, and then making a plot, so a canvas on which to plot. A bit of housekeeping so that my code is not too long. So, oops, let me undo that. So my code is not too long. And then I'm using an imshow again with, as you see, some arguments that I've passed from above. So that means they'll be interactive. Setting a title that will also take in values from above so that we have the correct title depending on what we're displaying. Choosing a color bar that we want to show and shrink it to the right height. And then the projected lines, I'll explain those when you see the plot because right now it's really abstract. So I've built this function, but I've not called it. I'm not using it yet. So the next thing I do is I'm going to use, again, interact. And in interact, I'm going to pass all of those widgets and properties that I want to pass to that function. So the function is seismic plotter. Let me execute that. The function is seismic plotter. The widgets are color map, section, inline, crossline, time slice, and the input volume is this string down here. And so this is going to be the last part of this demo, so I'm finishing a little early. And so let me just illustrate what's going on here. So first of all, I can change my color map. So let's take seismic, for example, and that will update my color map accordingly. Actually, that's pretty garish, so I'm going to go back to grays because we'll see the inline, crossline, time slices better on there. Then the active line that you're looking at is the line that's on the outside. So right now it's red, which means we're looking at an inline. You also see that in the title. We're looking at inline 300. And indeed, if I scroll this, if I change this, it doesn't update automatically, otherwise it would be really slow. It's still rather slow, but then again, remember, we're looking at a seismic cube. And so now you've seen I've moved to inline 305. In green there, you see a cross line, and in blue, a time slice. So let's say I want to look at, I don't know, this cross line over here, 362. So you see we've moved there. I can now toggle on 362 and move to that cross line. And likewise, we could do that with time slices. So let's say I want to be just a little lower to start to see those faults. And then toggle the time slice. And there is my time slice 152 in grayscale with the correct amplitudes. So that brings me to a conclusion for this demo. This notebook, obviously, I will share on Slack, or actually I will add it to the GitHub repo and we'll share that link if it hasn't been already. In a couple of minutes, I'm going to be joining the conversation on Slack on T20 Mon Python. I hope to see you there. Those of you who are watching this now and in future, I hope you've enjoyed this. It's been useful to you and hopefully given you some inspiration to learn Python if you don't already know it. So maybe just a quick recap of everything that we've seen in this quick whirlwind tour of Python. So remember, we started assuming that you knew little or no Python. And I showed you that you could build some simple mathematics, simple operations in Python. I really skimmed over that because it was not meant to be a tour of the syntax. We then saw basically that we could take an equation from Wikipedia or from a textbook that we have, and we could write that equation in Python, write it in such a way that we could reuse it so that we don't have to rewrite it every time. and use that equation not just on a single set of data, but on arrays of data, right? We moved on from there, did some structural geology with Ramberg-Biot as well, looked at some nice plots that we could make. From there, we looked at some simple geophysics and discovered that you can actually put some interactivity in Python, as you see here on screen. We looked at the Welly library. That was really quite quick. There's a lot more in there. But we looked at how we can load a single well. Welly actually allows you to load projects of multiple wells. And then each well in that project behaves just like a well that we saw here. We saw that we could plot these wells up, we could QC them, we could filter the depths, we could have QC plots for them in HTML based on tests that we could actually write ourselves if we wish. And finally, we looked at loading Seismic. Now, with the big caveat that this Seismic cube we're looking at is obviously curated and clean, you won't be surprised that it can be a little harder to load a Seismic cube in Python, but it's doable. And again, on Transform, there are additional efforts being made to make loading Seismic into SegWi even easier. So I really hope you see how far we've come. If this is your first introduction to Python, well, you're welcome to the Python world. You're welcome to the software underground. As I said, whoever and wherever you're from, I really want to insist on that in these crazy times we're living. I hope we'll see you in the rest of the tutorials this week. There's a lot more going on. There are some good tutorials for beginners, for instance, from Thomas Martin. There'll be links that you can find on Transform 2020 and Transform 2020 tutorials. Perhaps we'll put those links in this channel as well, just so that you can see them. And yeah, there's a lot more going on this week. So stay tuned. Thank you for following, and I'll see you online. That's it. Bye-bye.